So this lesson in AP Physics C looks at rotational dynamics and situations where the object is going to be accelerating. So we're no longer in equilibrium situations. The acceleration could be linear acceleration or rotational acceleration. So the problems for torque acceleration basically fall into two categories. One's where slipping is involved and where there is no slipping. The no slipping case allows us to use the bridge equations. The slipping case may allow us to if that's a boundary condition. So what is slipping? Okay, the bridge equations basically are the linear is equal to the rotational times r. Okay, and so these bridge equations apply when the object is not slipping, because when a wheel has rotated through one full rotation, or 2 pi radians, it has traveled the circumference of the wheel, 2 pi r. Okay, and because everything is linked via calculus, the linear is simply going to equal the rotational times r. We've seen the bridge equations in the kinematics slides. Okay, but when objects slip, the linear situation simply doesn't match the rotational situation, okay, because the object could be spinning but not moving, or vice versa, it could be moving but not spinning yet, okay. So when there is no slipping, okay, so here's a couple of situations. The object may rotate in place while the surface or a rope attached to the object may move, or the object may rotate along the surface, okay. So in this situation, okay, as the weight falls, the pulley rotates. So as the weight falls 2 pi r 2 pi r distance, the circle has rotated 2 pi radians. Similar to when the object rolls along the surface, it's gone 2 pi r and rotated 2 pi radians. Okay, so when there's acceleration, implies that there is a non-zero net torque. So the object is going to accelerate. So for instance, I have a mass m which is wound around a disk with a moment of inertia I. Okay, and it has a small axle and a big axle, but we're only attached to the small one, radius r. When we release the mass, okay, we need to find what the acceleration of mass m is. So this is kind of like a pulley problem that we saw before. And remember, because we have acceleration, what the torque is being provided by the tension in the rope. And the tension in the rope, when it is accelerating, is not simply mg. That's a very common misconception. Okay, the tension in the rope when it's still, okay, when it's in equilibrium, yes, the tension then equals mg. But in this case, it's not, because I'm accelerating. So therefore, the tension is going to be mg minus ma. Don't forget to draw the free body diagram there. Okay, so we have rotational equations. My net torque, tension times the radius, is equal to I alpha. Okay, and I have the linear force equations that basically find out what tension is, mg minus ma. Okay, since the bridge equations hold, alpha is, I can replace alpha with acceleration over r because I'm interested in acceleration, okay, not alpha. So if I make that substitution and solve for a, I find that a has the answer shown on the bottom. Okay, so this is a situation where the net torque, the rotational equation, and the linear equation must be used along with the bridge equation. Okay, so in angular acceleration cases, okay, in cases where the object is rolling down a ramp, the rotational torque comes from friction, okay? If it's a frictionless surface, sometimes you need to be a little bit careful. They might try to trick you on that. If there's no friction, there's no torque, okay? So in this case, as the object rolls down, okay, the linear equation is still force of gravity, mg sine theta, minus the friction, mu mg cosine theta, okay, mu fn. And that's going to equal mass times acceleration. The rotation equation is still torque, the friction, times r is equal to I alpha, and because there's no slipping, it's a over r. Again, making the substitution, I find that my acceleration is now 2/3 g sine theta. As you would expect, it will be less than what it would have been if there was no friction. Friction is always going to slow you down. And in this case, it slows me down to 2/3 g sine theta. It's only 2/3 because my object was a disk that has a moment of inertia of 1/2 mr squared. If it was a ball or a hoop or something else that has a different I, it would have a different A. So don't just memorize that equation. So here's something for practice, okay? I have a bar with mass m and length L, and it's allowed to pivot around one end, and it's held horizontal and then released. Okay, the moment of inertia for a bar around its end is 1/3 ml squared. We've seen that before. And the question is, what is the initial linear acceleration of the end of the bar after release? And the question afterwards is, why is the angular acceleration not constant? Okay, as it falls, why does my angular acceleration not stay constant? Okay, so try that. Okay, so rotational dynamics with slipping. Okay, when slipping is involved, okay, we can no longer use the bridge equations, but the linear dynamics and rotational dynamics, those are just Newton's laws. We can still use those equations. Okay, so here's a problem. Okay, I have a cue ball. Okay, this is billiards or pool. A cue ball is struck straight, giving the ball an initial linear velocity of v sub 0, but the ball has no rotation. Okay, and so this is a case where it's slipping. If it's not rotating but moving, that's where a situation where the linear doesn't match the rotational. But friction between the ball and the table acts as a torque to make the ball spin. At some point, the ball is no longer slipping because rotation has increased while its linear velocity has decreased. And so if we wanted to find what speed the ball would eventually have, this is how we would do it. We would set up the linear equation that says my acceleration is friction over the mass of the ball. Okay, and then my speed would then be v equals v0 minus at. Okay, and from a rotational standpoint, okay, my angular acceleration is going to be force times radius, the torque, divided by this moment of inertia I. Okay, or basically, since alpha when they match up will be a over r, and then my omega has to equal alpha t at that point. Okay, so the moment of inertia of a sphere is calculated to be 2/5 mr squared, and then I can solve these problems to find at what velocity, at what speed effectively will the two objects match. Okay, thank you very much.